Hi everyone, my name is Hesam. I'm here to talk about pyCuVSLAM, some of my experience accelerating SLAM systems, and also a lot of the tool sets that NVIDIA provides for robotics. Robotics is a big focus of NVIDIA, and I'd like to basically talk about all the different tools that NVIDIA provides to be able to accelerate development. So I'll talk about why visual localization, what is a visual localization system, and then I'll talk about pyCuVSLAM, and then also go into some of the other NVIDIA tools provided for robotics. So why do we want to have visual localization? So the reason that we'd want to have visual localization, a few algorithms that would benefit from visual localization, for example, would be robot control. So let's say higher frequency robot control, 20 hertz robot control. Or if you want to have some sort of a world state propagation algorithm. So you have single sensor measurements, let's say depth estimation, movement, and you want to be able to integrate this so that you can have some sort of a local perception system, maybe a safety system that makes sure that you don't actually collide with anything. You want to have global localization so you know where your robots are. You want to be able to command them to go from one place to the other. You want to understand the world, like for example, let's say a warehouse or an office space. And then also you need localization for example, creating nerfs, Gaussian splats, building a map for your, let's say, warehouse SLAM system, et cetera, et cetera. So the reason that we want to do visual localization again is because cameras are cheap, they're reliable, high fidelity, and they're widely used. They have very large field of view, and most applications use cameras anyways, right? So if you have a robot, that robot is going to use cameras for semantic understanding of the world. It reduces need for synchronization with multiple sensor modalities. Even though LiDARs are great, multiple sensor modalities are great, you want to reduce the amount of issues that you have. For example, some of the long tail issues you see when trying to deal with cameras versus LiDARs is that LiDARs are extremely rolling shutter, a single pixel at a time, while cameras, at least, for example, have scan lines, rolling shutter. So it's a little bit easier to deal with that. Ego motion compensation, for example, needs to be taken care of when you're talking about LiDARs versus cameras. You don't have to worry about as much. So some of the cons of visual localization, you need to have illumination and you need to have texture. I'll, for example, show some examples of stereo networks that are able to actually use priors that were learned during training. But flat surfaces, if you don't have any texture, you can't understand what's going on there. Versus LiDARs, for example, you can actually measure a flat surface because you're actively illuminating the flat surface. Of course, also when you have large images, lots of data, lots of pixels, lots of compute cost and bandwidth cost. And also, of course, you can have failure modes. So I'll talk about what is a visual localization system from the perspective of a person that spent a few years in production robotics. So just the algorithm is one part of it, but there are a lot of other things that come into consideration when building a visual localization system. I wanted to also bring this up so that you have a little bit of experience and you can understand how such systems are actually deployed in the real world. A lot of the time is actually spent on sensor, picking your sensors, understanding the interfaces between your sensors and your compute, spending a lot of time on the middleware, basically enabling you to get the sensor data into the algorithms, execute the algorithms, then pass the data from one algorithm to the other, and on and on. And then, of course, there's the part that we're all familiar with, which is the state estimation. And then, so there's a real-time component to these systems, and then there's also an offline component. So let's say offline would be something like map creation. So you go into your warehouse, you capture data, maybe you're estimating odometry, and you're even doing loop closures, but you probably want to do some sort of basically offline processing, map creation, and maintenance, basically. And then, as this gentleman mentioned here, calibration is also a big, big problem. Both initial calibration, knowing that you have a good calibration, encoding this calibration, and then maintaining that calibration over time is also something that's difficult. During development, actually, a lot of your time is also spent on finding the right ground truth, getting the right ground truth, collecting a lot of data sets, and then also calculating the right metrics and reporting those metrics in a way where you can detect failures and improve your system over time. Yeah, so some of the problems that you see in the real world are, for example, like I mentioned, sensor selection, but also making sure that you get the data at the right time, at the right frequency, at the right quality. So, for example, drops of frames, that can be potentially a big problem. Making sure that you have low jitter and low latency when it comes to the actual sensor stream. If you want to have a guaranteed execution of your, let's say, safety algorithms. Synchronization and timestamping of multiple sensors becomes a difficult problem, especially timestamping across large distances. Like, for example, let's say on an AV, timestamping and synchronizing everything. It's very difficult to actually guarantee sub-millisecond accuracy and quality of that timestamping and synchronization. Also, again, I mentioned calibration, arbitration. A lot of the long tail in bugs in autonomy systems is actually under unusual conditions. So let's say your compute spikes, a few of your algorithms have compute spikes, then this causes other algorithms to have issues. It's hard to make sure that things gracefully degrade. Introspection is important. In those cases, for example, you might be able to record the data, but that data recording actually causes your system to change, so you're not actually able to debug the issue. So a lot of these things, these are the types of things that can take a few engineers multiple weeks to try to figure out. And then you're validating everything in an ongoing manner. So like I said before, you're creating an infrastructure to be able to make sure that you're able to test your system, and then be able to basically reproduce these tests so that you can understand whether or not you're regressing or improving. And then some of the difficulties in this case are, it's very difficult to actually validate or have a suite of validation tests that, for example, bring in the arbitration issues that I mentioned, right? So like these very long tail issues are hard to test. So oftentimes you also need to, run a lot of on-device testing. So algorithm development is a small portion of the total development time. And yeah, long tail of problems is typically a lot of where your effort is spent. Actually, if you look at most teams, you have like 2-3, let's say in a SLAM team, you have 2-3 algorithm developers, and then there's like a supporting 7-person team that actually does everything else on top of it. So since this talk is a little bit about compute or accelerating SLAM, I'll talk about this. I spent a few years working on this, but I won't go too much in detail. So there's two big chunks of compute. There's dense operations. So let's say front ends, feature extractors, old school feature extractors, deep learning models, image processing, also even dense factorization, or let's say vector comparison for loop loaders. If you have your vectors for each image, you need to basically go through your database and compare it. So all of those are dense operations. Those are relatively easy to optimize, and they actually take up a significant amount of your compute, potentially about 50% of your compute. And then the rest in these state estimation algorithms, especially in bundle adjustment-based systems, a lot of your compute is also spent on the sparse operations. And in this case, being, let's say, linear solve. So you have AX equals B. If you're trying to solve your AX equals B problem to get your next estimates of X, you have to perform sparse operations. These can be solved either through factorization, like Cholesky factorization, or iterative methods like PCG, preconditioned conjugate gradients. PCG methods work better once your problem starts to get above about 1,000 parameters, but there are also a lot of design decisions. PCG requires preconditioning, right? So determining what that type of preconditioning is something that requires development. And also, of course, depending on the floating point precision that you use, you might have different problems. Like I said, this is a very complex problem. If you're looking to solve this problem, just make sure that you measure the compute of your whole system, and you actually make sure that you're solving a big part of the compute, because sometimes actually the dense operations end up being much more expensive than the sparse operations. So just make sure that you're spending the right amount of effort trying to optimize that. I'll talk about pyCuVSLAM a little bit now. So pyCuVSLAM, it's a project that's been, cuVSLAM is a project that's been going on quite a while at NVIDIA. But recently what we did was we tried to actually wrap it in Python so that you could use it more easily in robotics and also in deep learning training. It's very simple to use. You can basically pip install it. We're working on making the pip install a little bit easier. You have to actually pip install to a specific file that you provide, but we want to make it a little bit easier to install. But basically what you do is you instantiate your tracker and then call track, and then you get it posted out. Post quality is quite high. This is a visual odometry system. It's not necessarily robust against illumination changes and things like that, so just treat it as that. And it's very performant, 200 frames per second, multi-camera, and highly efficient, as I mentioned here. So pyCuVSLAM is the Python version. We also have a ROS2 node that's a little bit older. We recently published a technical paper. There's a few bugs in there. We'll fix it. And then there's a blog post here. I think what I could do is I can give you a link, Alejandro, of this presentation so people can look at it and click on the links later. Yeah. So yeah, what are the benefits of multi-camera? So this is basically at the top, you're seeing the input images. You're kind of seeing a visualization of the robot here, the features here. And then this is basically the comparison of 1 camera, 2 camera, and 4 camera visual odometry. You can see that it's being occluded and it's still operating well on the 4 camera case. Yeah, you can occlude more, and you can see the different cases. For example, the 2 camera and 1 camera are failing. Also, the quality is significantly higher. The post quality is significantly higher in the multi-camera mode. Yeah, so start up. Okay. We have another 15 minutes, 10 minutes. I'll go into what NVIDIA offers robotics for different types of basically tasks. So looking at the high level, basically some of the problems that we're trying to solve in robotics, first it's the data problem, as we mentioned before. It's difficult, as Angela was mentioning before, it's difficult to actually capture real world data. So one of our strategies is actually to basically create simulators that are able to basically generate the data for you. The other strategy is actually basically generating data through, let's say, foundation models or providing augmentation. So basically you generate, let's say, a simulation scene, and then using, let's say, an augmentation model, you actually change the appearance of that augmentation model with a text prompt. So data is one strategy at NVIDIA, basically trying to accelerate robotics. The other is basically infrastructure. We're well known for this. Of course, CUDA, Warp. I'll introduce Warp to those that don't know about it. Also middleware, we're supporting middleware so that this middleware runs well on our hardware. So Holoscan, I'll introduce that, and Isaac Ross. We've been supporting Isaac Ross for a few years now. And then we also have tools to make training models easier, and also actually commercially licensable models. And then also, of course, NVIDIA does a lot of research in perception and robotics. And then we also build workflows to enable people like you to generate data, for example, using Mobility Gen, Mimic Gen. So Isaac Lab and Isaac Sim, if you're not aware of it, it's a GPU accelerated simulator. Isaac Lab is a robotic learning framework. Mega is something that we're building for large-scale simulation. This is more related to companies, but let's say imagine if you have a warehouse that you want to deploy robots in, and you have 100 robots. You would like to basically simulate all of that. You can do that with Mega. Something that might be interesting for this group, Newton, is something that we're developing. It's going to be a differentiable simulator. So not only can you differentiate through your cost function or what you define, but also the physics of the actual world, you can differentiate through that. So you get a signal from that too. Something that's really interesting is Warp. Warp is basically a spatial computing framework. It allows you to define mathematics, and then it just in time compiles to CPU and GPU code. And it's also differentiable. So you might be able to actually implement a SLAM system using this and have it JIT to GPU code. Something that, I've handwritten like a full SLAM system and offloaded it. This makes it so much easier. As I mentioned, middleware. So middleware is quite complex. It's about launching processes and threads, handling sensors, transporting data in between, allocating compute and memory between the different processes and threads, and of course, providing diagnostic signals. We currently support Holoscan and Isaac ROS 2. Holoscan allows you to basically have real-time guarantees, zero copy from your sensors into your GPU, and also long-term support. 10 years, actually. The core functionality is supported for 10 years. And it's been used for years in medical applications, and we're now bringing it into robotics. We have a lot of accelerators on NVIDIA Jetson platforms. So we have a programmable vision accelerator. It's a DSP for image processing tasks. We also have an optical flow accelerator, so traditional Lucas Canare optical flow accelerator. And then, of course, we have the GPU and some libraries that you might be interested in would be cuBLAS, cuBSS, cuSolver, Warp, of course. All of these can be used to basically implement, for example, backend SLAM systems. And then there's the Tau toolkit. Tau is basically a toolkit for both quickly training models and also providing pre-trained models. So, for example, taking Dino V2, and actually we've taken that and we've retrained it with commercially licensable data so that you can basically use it commercially if you'd like to. Suggest going to this website. There's like hundreds of networks that we've retrained basically. Some very, very interesting research coming out of NVIDIA, recent research. I think one of the most important ones would be foundation stereo. It's at the quality where you can almost assume that this is ground truth. Very, very high quality, as you can see, very detailed. I suggest taking a look at this. We're actually using this internally for a lot of things. Another model is L4P, basically video encoding in, depth optical flow motion segmentation poses 2D tracks and 3D tracks out. Something else that we've found that actually is very interesting is AM radio. So basically kind of replaces Dino, V2, Clip, and SAM. And actually we've seen that it generalizes better. We've tested some downstream tasks and it generalizes better than Dino V2 in many cases. That's also something I would recommend taking a look at. We also have, for example, workflows for generating data. This might be somewhat related to, for example, Tartanair. Maybe Tartanair can use this as an example. We don't have as many assets in here, but you can basically create randomized navigation trajectories, basically. There's also something called MimicGen that does that for actual manipulation data. So one of the things that I mentioned, so we can have a simulator, and the simulator can generate some set of data. You would have to have the assets. You would have to configure the assets in different forms. One of the things that we do here is actually we take that simulated data and then we augment it using a text prompt. You can see that this is actually this scene right here that's generated by Carla has been augmented to look very different. Lighting has changed, even the structure of the scene has changed. This allows you to not only generate data, but also augment that data so that it looks visually different, especially for downstream tasks. Maybe perception tasks might look at the details too much, but downstream robotics tasks, you want to make it invariant to the scene. So another example is just using a simulator here, object level simulation, and passing this as an input into the network. We've generated this visual scene. So as you can see, we've increased the visual fidelity significantly. And this is coming with a text prompt. So it's been conditioned by a text prompt. You can condition it to be in Netherlands, right? This is in Paris, most likely. Yeah, so you can basically do this type of augmentation. We also have neural reconstruction. Both we've done NERF and also capture sliding. And essentially what you do is you basically capture your data, you reconstruct the data, and then you actually, for example, instead of going through the left turn lane, you say, okay, what if I go one lane to the left, right? So basically you can generate the data and then render more scenes from that data. So that was some of the simulation and data augmentation tools. And then we're also looking at, we're working on the GROOT project, which is essentially a research project that tries to solve the single image in, single command in, action out. So basically a fully end-to-end system, including running this on device. But some of the things that come out of this that are useful for people would be, for example, workflows for teleoperation, the manipulation data generation that I mentioned, mobility data generation, whole body controller, and some perception networks. If you go to this address, you'll see a list of everything. Yeah. So one question that I have, I think one of the things that, based on my experience, I've been kind of asking myself is, what level of detail and what information is required to enable the most amount of downstream tasks, and the downstream tasks being, local navigation, global navigation, and fine and coarse tasks. So, not all tasks, for example, require extreme amounts of detail, right? So like a global navigation task requires very sparse occupancy information. But the task that requires you to, for example, screw a bolt onto a nut or a nut onto a bolt will require very, very detailed perception capabilities, right? So coming from a localization and, let's say, perception background, the question that I have is like, what is that representation? Can we actually define something like that? Or do we need to have multiple different ways of perceiving the world to be able to basically, solve specific tasks? If we can have just a single representation that's detailed enough and has enough information, that makes our lives a little bit easier. And for example, also, can this representation be open vocabulary? So can we, for example, encode all the knowledge that has been learned in the language space into the visual space, right, or into the perception space? Because if that's the case, then you can then give more general commands and say, hey, pick up that cup next to that book, right? Instead of defining a system that basically has to have rules-based essentially, procedures to actually solve that problem. So that's what I wanted to kind of leave everybody with, because that's something that I'm thinking about right now as I, see all the different problems that are trying to be solved in the robotics field. Cool. Yeah, that's it. Any questions?
Any question?
Yeah. Thanks for the presentation, and especially the first part, that very practical aspect of deploying SLAM systems and maintaining them. I also have a couple of years of experience from Silicon Valley, where similar problems, where I experienced similar problems. But the question I wanted to ask is about parallelization of backend on GPU. You mentioned that there are a couple of packages that, there's this Warp, I guess, or CUDA, which can be used for backend parallelization, but beyond this SLAM system that you showed from NVIDIA, are you aware maybe if there are other SLAM systems which utilize this parallelization? I'm talking about specifically about backend, not about front end, because I guess 90% of Silicon Valley runs on CUDA, but when it comes to front end,
Yeah.
Sorry, when it comes to backend, yeah, what is the adoption there?
I know cuDSS, I believe we have a backend for cuDSS in Ceres. But the thing is, the linear solve, and then there's also the residual calculation, right? So it's very domain specific, even problem specific problem basically, right? So like, do you add your residuals offline? Is it a batch problem, or is it like a large scale, let's say, odometry?
I mean, I'm talking
system.
right now about real-time systems, so yeah.
Yeah.
It will be like odometry.
Yeah. The reason that I say that is that a lot of your compute can be spent on actually creating the residuals, right? Like adding the new factors into your system, memory allocation and things like that. But I'm not aware of such a system, but this is because it's, in my opinion, it's so domain specific. It requires so many design decisions. And like basically it's one of those things where you first solve the easy problems, and then you probably spend a few years solving the nitty-gritty of the problem. So to me, that seems like a person or a startup that is dedicated to this would spend a couple of years making some design decisions, and then actually like a couple of years down the road, those design decisions have some limitations, and they'll have to basically refactor. But yeah, based on my experience, I think it's it's a quite complicated problem, and that's why I think people haven't really solved it yet. Because again, like there's other problems to be solved that are probably more pressing than like trying to accelerate this to like the 100%.
Thank you.
So we have 3 more questions, so 1, 2, 3.
So for the continuous transfer model, if I like give a video from robot and after I do the transfer, will it keep the geometry consistency?
Yeah. So it has a bunch of controls, what are called controls. I suggest just searching for Cosmos transfer online. You'll find a lot of resources, but you can have, for example, depth control, edge control, other types of control. And what control does is basically you weigh the controls also differently, and what it does is it tries to make sure that control is abided by. So like depth control, for example, says that pixel should be at that depth, or edge control says that this edge should stay consistent and sharp. So that basically makes it so that you can control what you want to actually keep in the image and what you want to augment.
And does it like suppose like add dynamic like pedestrian or something like that? Dynamic object like pedestrian and like animals inside the thing? Okay.
That would probably geometry, from what I've seen, and this is of course being developed and new iterations are coming out, but you want to simulate and render your own geometry, and then, for example, tell it to change the appearance of the dog, not necessarily add a dog, but like change the appearance of the dog, for example. But that's just based off my current experience, and these things are being developed, and you can potentially see that change. But here you can see that the geometry has actually changed, right?
Yeah.
So yeah, but it might be a little bit less controllable if you try to change the geometry without giving controls.
Okay. Thank you.
I want to start addressing some of the question that you had in the last slide. I come from much more of a planning and controls approach, so I've been using perception routing systems rather than developing them. It was really nice to see on as I cross Visual SLAM, you can get a covariance associated with the pose estimate. But in a lot of mapping systems, I don't get some notion of uncertainty. So is this something that you guys are interested in developing? Is this a direction that you're pushing? Because if I want to do a path planning, or if I want to do obstacle avoidance, I need to know how uncertain my perception is. And I don't know whether anyone has been really working on that part of the problem. I don't know if you have thoughts on this or different resolutions for this.
Yeah, I think we definitely have, for example, previous speaker, she's worked on this probably quite a lot. I think even uncertainty estimation coming out of a traditional SLAM system that's relatively unreliable in many ways, actually. So I think it's still a research question on how we can actually output reliable uncertainty.
Probably a tricky question. I know that NVIDIA is a company, but I was interested in pyCuVSLAM and was wondering, do you have a plan for open sourcing it, or do you plan to keep it close?
No active plans to open source it. Do you think that there's any? Should we open source it? Do you think we should open source it?
I think there are many pros. Also for you, open source does not mean free.
Yeah.
But I think having some more noble, end to control, to tweak it, to customize it. As you said, every problem is custom and need a specific study application. So I think probably could be beneficial for many practitioners, researchers that need to apply it to very specific problems.
Yeah, no, that's great feedback. You can get, for example, the feature selection output. So you can actually get the feature tracks out. If you look, there's a data structure called observations, and then there's also the 3D points that you can get out. So, basically the only thing that's left is just the backend, which is relatively off the shelf, basically it's 11 Weimar chord solver in the backend. It's not, very. So you can also actually use that. I think the real strength of pyCuVSLAM is actually mostly in the backend, and even actually the 2D matching, essentially. It's been tuned over the course of many years and refined, basically. So if you just use that, you might get most of the benefits.
And there are bindings also for Python, or you need to go C++ for that?
Yeah, no, actually pyCuVSLAM is that binding.
Okay.
Yeah. So basically, this is how you use it. Rig is your calibration. Basically, config is your actual, configurations, as in, non-calibration configurations. And then you create your tracker, and then you pass a timestamp and a set of images. You get your poses out. And you can find it at NV Labs pyCuVSLAM.